Good afternoon. Welcome to Krishna's classroom. Last time we proved the Lusin theorem, which in fact had the content that measurable functions can be nearly a continuous function, or almost everywhere it is equal to a continuous function. Okay. So that is the relationship between a continuous function and measurable functions. So they are nearly continuous functions. Now that's the meaning. Nearly in the sense of measure. Now, if you examine the statement of the Lusin theorem, then it is clear in what sense we are making that statement. Now, what we want to look at in this talk is a corollary to the Lusin's theorem, where we start with the basic assumptions of the Lusin's theorem. So, what are the assumptions? So, we assume the following. X is a locally compact Hausdorff space. Now the X script M mu is the measure space determined by the NISER summation. So the same topological scenario that you have as in the Lusin theorem, that is X is a locally compact Hausdorff space. Now, what we assert is the following. Now we assume, suppose f is a complex measurable function on X, comma A is contained in X, mu of A is measure of A is finite. And f of x equal to 0 when x does not belong to it. So that means outside A, the function f is assumed to be identically 0. And measure of A is assumed to be finite. Of course, that really uses the fact that A is requires the fact that A is measurable. Okay. Now let epsilon be positive and assume that means we are coming to the condition stated in the theorem. So these are the basic assumptions that you have. It is the same as that you have with the Lusin's theorem. with the following conditions on f. That is, f is a complex measurable function on x. A is contained in x. Measure of A is finite, and f of x equal to 0 whenever x is not in A. Further, let epsilon be an arbitrary positive number that is a fixed one that we are going to use, and assume mod f is less than or equal. Then, by Lusin's theorem, here for each n there exists Gn, which is continuous function with compact support on x, CCX. These are continuous functions with compact support. Mod Gn is less than or equal to 1, such that mu of En is less than or equal to 2 to the power minus n where En is defined as set of all x belonging to x such that fx is not equal to. That means for each epsilon chosen as 2 to the power minus n, you have this result. Okay, that is the application of Lusin's theorem. Says there exists a, for each n there exists a Gn which is CCX mod C less than or equal to 1, mod G less than or equal to 1, such that mu of En is less than or equal to 2 to the power minus n, where En is equal to, is defined as the set of all x for which g fx is not equal to gx. Now for almost all x, it is true that x lies in at most finitely many. How do you come to this conclusion? This comes from the following result. So if Ek is a sequence of measurable sets, it's a consequence of the following result. In X, such that sigma measure of EK is finite, infinity, then almost all x in X lie in at most finitely many is. This is the result that we are making use of. Okay. So on the basis of this result, see that for almost all x, it is true that x lies in at most finitely many. It's just a consequence of this result. Now, this is the condition that is to be satisfied. Namely, EKs are measurable and sigma k running from 1 to infinity mu of EK is finite. Now, you see that the sort of the way in which En is taken, it is taken as mu of En is less than or equal to or minus n. Therefore, this particular condition is satisfied. And a consequence of that, you see that x lies in at most finitely many. Now that actually settles our result. Okay. For any such x, fx is equal to gnx for all now that's a consequence of this, as you can see, immediately apply this to see that x belongs to at most all x belonging to x which lie in at most finitely many EKs. So beyond this finitely many EKs, you see that from some stage onwards, x does not belong. What is the what is the what is the implication of that? It implies that fx is equal to gnx for all large enough n. What does it mean? This implies fx is equal to with n tending to infinity gnx. Now, okay. So that is it's a consequence of this result applied to this scenario that you get this. Okay, so that is a immediate corollary to the Lusin's theorem. Now, what we plan to do next is the Vitali theory Then we do it in our next lecture. But before that, we want to recall some small results, which is about what are called lower semi-continuous functions and upper semi-continuous functions. Let us take the definition. Let F be a real or extended real. That means may take value plus 1 or minus 1. Sorry, plus infinity and minus infinity also possibly on some at some points. Then F is said to be semi-continuous lower semi-continuous if the set of all x for which is open for every alpha. Further, F is said to be upper semi-continuous said to be upper semi-continuous if the set of all x for which less than alpha is open for every alpha belonging to. So these are the two class of functions. A function which is both upper semi-continuous and lower semi-continuous is said to be continuous. Now you recall the definition of a continuous function. What will be the definition of a continuous function? For all open sets alpha, for all open intervals. Okay. See, F is said to be continuous if F inverse of alpha beta. Alpha beta is an interval. in open interval. Now you can see that this corresponds to two things. One, it is lower semi-continuous, it is upper semi-continuous. Both these conditions are simultaneously satisfied by f, then you say it's a continuous. Okay, so that is the function. And upper semi-continuous. If set it continuous, you can check the equivalence of the previous statement and this. Right? Now let us look at some examples. Let open. Consider the characteristics function what is the nature of f? One can show that f is similarly. Let K a closed set. Is upper semi-continuous. Upper semi. Now these are two examples, which we shall require to use later in the proof of the theorem. Now one can easily try to prove this result. It's not difficult to prove this. So let us do one of them. Then we have equal to 1 for x belonging to B and equal to 0 x does not. Now this is the definition of the characteristic function. So we prove that V is lower semicolon. Now this is true because consider V is lower semiconductors. F is lower semiconductors. Now let us look at the following. Make the following observation. Observe that the, the set of all x for which alpha, this is equal to x for alpha less than or equal. Because it takes either the value 1 or, see, this is the scenario, takes the value 0 or 1. Okay. So suppose you take any alpha which is less than or equal to some alpha, what happens? Fx greater than alpha would take value both 0 and 1, therefore this is equal to x. And how far it can go? It can go up to 0, okay, but not including 0. So if then fx greater than 0 is again taking the value both uh, then fx greater than 0 is also equal to the whole of x, because it takes the value 0 or 1, right? So this is open. Now let us take the value alpha for this is equal to V if less than or equal to. Suppose alpha turns out to be greater than 0, then what happens? It does not take fx is not equal to 0. Therefore, it can take, it takes value 1. So, the up to this, okay, that is when alpha is takes the value from 0 to 1, 0 excluded, to see that the set x or fx greater than alpha is exactly equal to b. But b is open. So now you take the remaining function. This is empty whenever alpha less than 1. For the remaining values of alpha, you see that this particular set is an empty set which is vacuously open. Now similar example, now similar argument you can use. Similarly, K closed in X can be the condition for upper symmetry. What you need is realize is less than alpha. You will have to split it up into various sets. You can show that for all alpha coming to R, this is open. This is what you do. That's very easy to check. Okay. So these results are what we require in the proof of the Vitali-Kara-Theorem theorem, which we have already stated earlier in one of our lectures, and we are going to prove now. Thank you very much. It's very short. It's a